It's foolish mathematics.
Nothing.
Trouble.
Don't worry. Partial least squares equation. In a sense, it's similar to the principal component equations where there's a difference in that principal component equation, basically we find the best linear combination in the input variables. Okay. Using the principal components method. Because the criteria of that is like you try to redistribute the total variances in the input variables into the most important one followed by the second most, and so on. Most important one means to find the one in the particular directions that account for most of the variability. Actually, we did talk about principal components analysis. But actually, with a two-dimensional example, it's like this. This is just a very straightforward, okay, understanding of this so-called principal components analysis. This works. We have the sort of causal data. Let me just take the two-dimensional case here where you have say x1 and x2. You have these two variables in case of these input variables. Okay. One way to look at the variability in this data set is look at the variability in this direction. So here we have the variability. Here this is variance of x1, right? And also look at the projection. Hope that this is good. And also look at the variability in x2 direction. And a way to define the total variance that we see from this data set is just trying to add up the variability. So actually, by doing so, we are not taking into account the covariance between these two. Let's look at the total variance. Okay. And the idea of the principal components try to redistribute these total variances into the direction that capture the most variability. In a sense, you can see that here. The capture the most variability is by looking at this. If you tilt this data cloud to a certain angle, you can see there's a direction that will come from most variability. Yeah. In fact, it's in this direction. If you look at this one, so basically you kind of rotate your data set into new variable. Here, this is x1 tilde. By relocating the center and also do rotation. And you can see that in this direction, okay, this direction will account the most major parts of the total variance of this one. Okay, so here this is the result is this variance of x1 tilde plus the variance x2 tilde. Okay, and most likely, if you look at this probably will account for about say 60, 70, or maybe 80% of the total variance, rather than just look at this direction. Okay, so here this direction is so-called. This is called the first principal component. So we can redistribute the total variances. Okay, So original variation, if you look at this two direction, probably this is 50-50 distribution. And now do this rotation, you probably have like a 70 or maybe 80 versus 20 distribution. And the idea of this principal component is that, of course, here this is only very low dimensional case. Right? If you consider this as high dimensional case, okay, if you are able to find the two directions that account the most variation in this high dimensional case, we just use the two information. And in fact, each one, this direction is a linear combination of x1 and x2. This is another linear combination of x1 and x2. So these are the two principal component direction of the input variables, and then regression principal component regression based by regression on these two directions. Okay? Because in general, we want to, if you have a high dimensional case, okay, let's say, what I plotted here is only the two dimension. Okay. So in general, you have p variables, and we distributed these total variances, and suppose that, of course, this in general probably this is not the case. Okay. Probably the first two directions already account for 10, and then you account for 80% for only the first direction, and these two combined probably already account for 90% total variance. Then we just use these two dimensions. So in a sense, this is data. This is dimension reduction. We reduce the data into only these two directions, x1 and x2. So from p variance reduced down to just two variance, okay, by very case. And there's a tremendous reduction in data. Of course, we also lost some information, right? It's probably about 10% loss in this total variance. But usually, this data approximation will be good enough to approximate this the features that you have in this input variable. Then you do regression of y versus this, and that's the so-called principal component regression. But the partially squared, slightly different, although the idea is very similar. It's like still doing the principal component, but we take into account both input variables and the response. Okay. So partially squared uses both the inputs x and the response y to compute the set of linear combinations, rather than just looking at x alone. Okay. Anyway, here these are algorithms. We don't have to just get into the details of that. Of course, here, what is this? This is partially squared regression. Okay. But we can have our response of, say, +1, -1, and predict the result, and again use the sign of the y, right, to get classification in case you have classification problem. So first, the inputs are standardized. Okay. So all the variables are standardized. Okay. The input variables, not the response. Okay. Input variable standardized, and we set initial value, okay, x j0. So initial value for the input variable will be the standardized values of these variables, and response also. Okay. With this, just have the mean values for that. Okay. So set response at constant, which is the average of the responses. Okay. And then we, for each of these components, basically just find the projection of the response onto the J input like this. Okay. And the partially squared direction is kind of you kind of predict actually the projection response onto the J's input. Okay. Basically, you just do a sort of one variable in a sense. You think about this like one variable regression, right? Okay. And this is the projection we have. So basically, that measures the strength effect of variable xj on the response for current stage. Okay. Of course, originally for m equal 1, when m is 1 and you have 0, that's using the initial value. So initial value, the strength of the initial variable on the response. Okay. In a sense, you measure the sort of main effect for all the variables to start with. Okay. And then compute the m's partially squared direction by finding this. Okay. See, actually, the idea is you just try to remove the effects of individual variables from the response, okay, and reiterate on refining the prediction. Okay, so then after that, it regrades y on Zm. So you look at each step, this Zm, this is linear combination, right? This linear combination of the input variable. Okay? So basically, at each step, you request y on the linear combination of the response variable, okay, and get an estimate of the coefficient by using this information. And you refine your responses, just update the responses by using this the regression result. Okay? Updating your response by that. Okay? Should we get into this detail then? So every step you're actually doing regressions on linear combinations of the response, okay? And refining that the result, okay? And you output at each stage the predicted response like this. Okay? So here, I think if you got I think I have an arrows in the earlier version of this class number. It's kind of modified this game. So you can theoretically you can just find all the fitted response from y1 to yp. Of course, but in predict we don't need to extract that many components. Usually, we want to find a low dimension representation result. Okay? So actually, the idea of this partial least square classifier is a classification problem. Use the indicator matrix for the responses. Okay, you can use 1, 0. Actually, you can also use a -1, +1, but use a sign as a result. Okay, and choose n components only, and use class that produce a maximum predicted response. Okay, either way, either use 1, 0, or you can use a -1, +1, and use a sign of the result. Okay. If you use the sign of the result, if the response is negative sign, then you assign has to say to class number 1. If you have positive response, you assign to class number 2. I didn't spend too much time on this, and there's only a very short example of partial least square. The result is awful in this case. Okay? It's partial least square. At least for this problem, okay? This is not the best classification method. Yeah, this is a class 15D.ask. I kind of added this. That was very simple examples. I didn't go after this. The result is really awful. You can see that. Here I didn't split the data into trend set and test set. I only just do examples of the entire data set. Let's look at the result. You need to load the caret package, okay? And it's going to let's put this many packages on. Okay, so this is actually a package that you load that of this other packages. There's a dependency on that, and there are also a list of suggested packages, and they will be loaded on demand. Depends on the command you use. Okay. Actually, you see that. You see this. One of this is for each, right? I mentioned this last time. This package. But actually, it's offer very simple backend for parallel processing. Okay. Some of these tuning problems probably need some parallel computing. So if you have a large problem, you probably need to do that. Okay. Basically, we start with this trend control method. Suppose here we're doing a cross validation 3 times. Okay. And each time is 10-fold cross validation. So here, repeat 3 times. Okay. We use a repeated cross validation. Okay. And the 10-fold cross validation was done each time, and doing 3 times. Okay. And return resample result, or the final result. and you estimate class probabilities. Okay. So here basically these are the set of parameters we set up there. And then we start out with scaling this. Actually, by default, this is simply just a scale comment. That's all you can do. This is seamless. The sim will produce this. You know, you can do this. Well, this is just an output variable, output new variable name size spacewide. You're going to accomplish the same result instead of doing that. What was that? Iris. Here we basically use the default method. The default method including centering the observations and scale by the standard deviation individually. So basically the same command can accomplish that. And the reason in this package is that this preprocess can do much more than just regular scaling. Right? You can also choose like there's a box task with power transformation and finding the best result, transforming the response. Okay? But, well, we're not doing that power transformation here. Actually, it doesn't make sense in this case because this is a classification problem, right? The response is classes, so we don't do power transformation. Okay, -1 and +1 or 1, 0. Okay, so here we just do a regular thing here. Okay. Now let's look at this is partial least square fitting here. Okay. Partial least square fitting has a component. There's a parameter called ncomp, C-O-N-C-O-M-P. Look at help documentation on that. Okay. I think it has a help documentation on PLS, I guess. PLSDA, forgot which one. Anyway, they have that arguments. And remember in the package carrot, they talk about if you have for your model the component to control. I mean the arguments, the parameter, the tuning parameter to control. You just precede that tuning parameter with a dot. Okay. So here this is an example. So here I didn't choose the default like tuning length of 3, and then in general it's 3 to the power of p. In our case, p is 1. There's only one parameter here, so there are 3 different values that by default. I choose not to use that default. I use like 4 different values for that. So basically, the tuning grid means that we PLS will fit with 1 component only, will fit with 2 components, fit with 3 components, fit with 4 components. So basically, we're indicating M. Ncomp is the M that we're choosing here. Okay. So that's the parameter. Okay. This is number of components specified in partial least square model. Okay. So here we choose this the tuning parameter between 1 component, 2 components, 3 components, 4 components. Just different this 4 different values. And for iris data, the maximum number of components you can specify is 4, right? Isn't it? There are only 4 variables. Okay, unless you add in your model, you add like second order term. If you really want to do that, okay, there's of course there's a way to do that, right? Okay, you can run a polynomial on this. Okay, here, only up to 4 components. Okay. Wait a minute. This is not right. Oh yeah. Sorry. Here I already scaled this down. So here this is x variable. Here. Okay. So we train on this data set where x is this, right? These are input variable. This is already scale input variable. Okay. And this part is our response of interest, right? So x and y. Okay. Method is partially squared. And the train control is given by this function. This train control is set up there. Okay. And the tune grid will be see here PLS at this variable capital N. Okay, with specified at 4 different values. So basically, we kind of fit this 4 different partially square model and try to choose one that is the best. Okay. So let's run this anyway. Takes about maybe 10 seconds to run that. So just give out some information. So you can actually see that when R does this one, okay, their package will be loaded on demand because of this PLS required package class, required package PLS. So actually they load that on demand today. Yeah. And then here, these are the results. It says talk about resampling, post-validation, tenfold, repeat 3 times. And here is no pre-processing. The reason is I already processed the data. So, okay, I didn't do this. Anyone try this out? They have the options called pre-process parameters. I tried both ways. They didn't work. Something is weird about that. I thought that you can just do it directly, but according to their help documentation. Okay, I tried both ways. One is provide options in the tune control. Not the tune grid, the tune control, the train control. Okay. The other one is provide this option directly in the tune function that both didn't work. So I don't know why. That's why I do it explicitly. I do the scaling explicitly, and then provide with this. Okay. But anyway, here this is part of output. Is talk about resampling result across tuning parameters. These are the final result, and then it says the final value used for the model was n equal 3. Okay. And by default, I guess internally they try to use parallel processing. Okay. They use this, okay. But since I didn't register for that, okay, there's a way to register for that. Execute this do-par expansion. There's actually a function within that. Within this for each, okay, do that. Anyway, this is not worried about this. Not a big problem. Okay. So the final values for the model use was n equal 3. So it suggests using 3 components. It's more or less reflecting what we learned from other type of modeling, like 3. Probably only 3 out of these 4 variables will play significant roles about classification. And the output shows the accuracy. This is our regular agreement rate. Okay. 1 minus agreement rates, of course, will be the error rate. Okay. And here, kappa. This is a kappa statistic. This Cohen's kappa statistics into basically something like this. Okay. It's sort of measure the proportion of actual agreements on that. Okay. The reason that some of this also suggests that they say that this is just the regular error rate didn't take into consideration, okay, randomness in the data. So it's sort of deterministic. Actually, some researchers argue that's not the case. But anyway, here, just an alternative for this kappa statistic would be this. Okay, this is probability. Oops. Roughly like this. Here, this is probability of agreement minus probability of random agreements. So you should extract the components where that happen randomly. Just extract that part. Okay, the rest will be the actual agreement between these two groups, and 1 minus probability. This is some statistics trying to measure this inter-raters agreements, meaning that you have 2 groups, right? In our case, of course, we have our actual members, and there's a classified members. This is like a 2 raters rate on that. Okay? So idea of this probability of agreement is the accuracy in this case. Okay? This part is measured by the accuracy. That's a 0.667. Okay. And probably a random agreement is that well, you look at the class. You first look at the class error rate. Okay. Maybe we should use an example of that. Okay. So let's look at our. Probably take the last one for example. Hope we can recover this information. Well, here we have 3 classes case. The definition I put out is just for 2 classes case. I don't recall what is the classes case. For two classes case, it is so-called Cohen's kappa. 3 classes case is called this is for 2 classes case. Okay? So there's a general measurement called I forgot about the formula for that. I know for 2 classes case, probably not appropriate for this case. Okay? Let's say you have 2 rate on say yes and no. Okay. Let's get one example. What is the class proportion of yeses here? This is 45 out of 60, so what is that? 0.75, right? Yeah. So that's the accuracy for this one, right? And for this group, let's say we find the other number. I'm trying to find a good example. So I put 75% also. Put different number, 15, 35. So 35 out of 50, that would be 70%, right? So that, okay, 0.70. And the total accuracy for this probability of agreement would be 45 plus 35 over the total. What is total number of observations we got here? I should come up with a better number. 110, right? So what is that probability? This is supposed to be this one, okay? So this probability is this, okay? That's probability of agreement, right? It's estimated by that, so that's the estimate. Okay? And probabilities of the random agreements is done by this, okay? Assuming that they rate this independently. So what is chance they both rate yes? So be 0.75 times 0.70, right? Isn't it? The first rater say yes with a probability 75%, right? The second rater say yes with probability 70. Suppose they rate independently, randomly. So you have probably the same both say yes would be 0.70 plus times 0.70. Plus probably they both say no. No. So they both say yes or about. Sorry. The chance the first one say yes is 0.70. The chance the second one say yes is what? 0.30. Sorry, right? Isn't it? I got this wrong. Okay, they both say yeses, right? And what is the chance they both say no? The first will say. I'm not trying to do it here. do this right? Say yeses. Let's see. This person say yes with probability of 0.7. Look at the other direction, right? Should be the other way around, sorry. Yeah. This person say yes with probably 0.70 as well, right? Isn't it? It's 0.75, sorry. Yeah. So I shouldn't do that. Okay, this is 0.75, right? Right? Okay. So no wonder I got this wrong. I'm not doing it. Okay. Now on same direction. So they both say yes with probably 0.75 times 0.75. The chance they both say no will be what? 0.25 9.25. Okay. So this probably is a random agreement will be estimated by that. Okay. So basically that's the kappa statistic. I couldn't remember the general form of that. Look at this definition. This phi is a kappa. Anyway, in the literature, see the opinion about whether accuracy or kappa should be used, they are not in agreement. There's a disagreement about using different things. And you can see I use the default, I use accuracy. Well, this package uses accuracy as default. So apparently the author suggests using accuracy rather than using that. This is default. Okay. About the goodness of the model. The final model says that they're supposed to be just 3 components. But even with this base model, you can see there's a lot of misclassified identities here, right? So you have 1 plus 5, you have a total of 23 misclassified identities. So it's a huge proportion, right? With error rate about 50%. Not really good result, okay? You can also actually see the accuracy did not improve, and then kappa did not improve. But while the standard deviation increasing, right? So that's why 3 components better than 4. Not only at the standard deviation for these 2 statistics, but also that with 3 components model is simpler. Okay? That's the only result I got for this. Of course, you can run, you can set different seeds while the results are slightly different. You can train as different study seeds. Okay, I'd like to move into unsupervised learning today. So that will be our next topic. I already put out the class notes 16 and 17. I need to reorganize this. Let's first look at so-called unsupervised learning and what kind of tasks involved in unsupervised learning. Supervised learning, primarily classification. Of course, that's not the only thing you can talk about. You can also look at supervising. You can also look at regression training as well. Okay? Those are supervised. Okay? And unsupervised learning involved, actually we already talked about at the very beginning of the semester. Okay, it's a machine learning task without a teacher. Okay, meaning that there's no definite answer to the questions, right? Okay, so it directly influences on the properties. Okay, and there are basically 2 major types of properties of interest. One is about relationship, the other one is about grouping. Okay. Clustering is about grouping, and there are other tools like relation, like association rules, and some other things that we talk about in the future. So basically, they directly influences on the properties on the population distribution based on the observations, observed vectors on the observation. And usually this involves a very high dimension of observations. Okay. High dimension means that you have more attributes than you have in observation. Okay. Like in this clusterings of genes, you probably have like a few hundreds of observations, but you want to look at thousands of different straight, right? Okay. So usually we involve with high dimensional data. So number of variables or attributes is often very high. And usually it's much higher than the number of observations. And there's no clear measure of success because this is unsupervised, no teacher run, so you do not know sort of the real answers to that, right? Okay. So the success is often judged subjectively by the value of discovery noise of the, so even though just effectiveness of the algorithm really depends on that. So oftentimes that this unsupervised learning, okay, calls for like several, run from several different methods and see if there's some kind of intersection. I mean, a common outcome from different methods. Okay? Usually we want to do that. Okay? Now these are some models for unsupervised learning. Association rules. This is study of relationship. Okay? For example, market basket analysis. I guess in the future I'm going to briefly talk about this in class note 18 or 19. I forgot which one. And correlation analysis and generalized association rules. R has packages which you need to install. It's called A rule. With or without it. Okay. And simply just by that. With S or without it. Okay. Maybe without S. Oh yeah, with S, okay? So A rules, this is a package that will just do this association rules, okay? Okay, example like market basket example, okay? Correlation analysis in this, okay? And cluster analysis is study of grouping, okay? Study of grouping rather than relationship. Okay? Examples are this hierarchical clustering algorithm, including divisive, okay? That's a top-down algorithm, including this agglomerative algorithm, which is a bottom-up approach. K-mean clustering algorithm, combinatorial algorithm, self-organizing map. We have a example in the future about some of these topics like self-organizing map. And there are other multivariate methods, study of relationship, including principal components analysis, which actually mentioned briefly today. Okay? And factor analysis, latent variables analysis, and the projection pursuit method. Multi-dimensional scaling is also another type. Okay? Now let's look at clustering. It looks like at first they are the same, right? Because here we are looking for groupings here. And in classification, we also do grouping, right? But there's a difference between clustering and classification. In classification, we learn a method for predicting the instance classes from pre-labeled classified instances. So we already know the correct answers, right? Isn't it? Okay. So here this is supervised learning. So like this example, the class identities are known for all observations, right? So in nature, you just try to divide this into two groups using some kind of rules, support vector, or any kind of rules that can come out as to separate this. Okay. I guess for this one, we can fit nice support vector machine over there, right? Okay. But in clustering, the nature, you try to find nature grouping for unlabeled data. I don't know what happened to my. So you see a dot there. Huh? Okay. Something is wrong with my. Did I produce this in R? Let me go back and check. Anyway, this is this graphics was contaminated. Anyway, the cluster, you take this n objects, all the objects are unlabeled, meaning that their identity are unknown. Okay? So you do not know the group identities, but you try to divide this into groups. Now even the number of groups is unknown, right? Okay. So look at the nature of groupings. I think this is more nature like it's the application in astronomy is like, well, how can you classify say the distant object as belonging to which star system or which galaxy, so this kind of thing. Okay. The basic types of algorithm for clustering is first type is hierarchical. The second type, maybe we just do this automatically. Okay. Hierarchical clustering. Basically, this belongs to the will be establishing a tree of objects and using a graphical representation, which is called dendrogram. It's like tree-like structure, and then you decide on what is the best way to cut down into just few groups. Okay? If you don't want to cut into too many groups, you don't want to retain too few groups. So it depends on there's certainly some things that you need to consider. Okay? And hierarchical clustering has like two basic different approaches. One is this agglomerative. Okay? So here this is bottom up. This is bottom up method. Okay? Building from individual object and up to finally you reach just one all the object within one big group. Okay? And the divisive approach, you start with all data sets, consider all observations that's from one cluster and start dividing that. Okay? You can look at the star and see it for example, the quadrant of the skies and see this is, for this area, okay, for this quadrant, and then I further divide into galaxies or maybe the final groups of that. Okay? The second type of algorithm would be partitioning. Okay? This will be distinct non-overlapping groups and iterative shufflings of objects, and that include k-mean clustering, okay, and among others. Okay. There's a particular software package called Cluster, which comes with a standard R distribution. This is already come with a standard distribution. You don't have to install that, right? So that means that package is really stable. It has a lot of different type of clustering method. Okay? I'm going to produce a class notes about introducing that particular package because they are different methods and kind of useful in there. About that. And there are other types of clustering. This algorithm about clustering using some fuzzy clustering and some overlapping clustering. So overlapping is kind of interesting that you allow. So in all other types, okay, other than this, okay, this partition and hierarchical. For any objects or observation in your data set, it can only belong to one cluster, okay? As the final result. Okay? You cannot have two different clusters share the same member. But in overlapping a cluster, okay, this kind of the share, well, I shouldn't say share. The particular member shared by multiple clusters is allowed in this overlapping. Sometimes this is nature, right? You could have any individual that take two different roles, right? It would be like an intersection of multiple groups. Okay? So this is kind of interesting result. Okay? I guess we cannot get into that far. There are algorithms about dealing with that. Okay? There's overlapping clustering. The usual clusterings we have seen is in the first two categories. Okay? This hierarchical or partition. This so-called agglomerative hierarchical method start with each object alone in it as one object, one group. And so start with capital N groups. So you have this many groups to start with. And then you start to group two most similar or two observations with the shortest distance. You group them together as they are coming from the same group. Okay? And then you kind of gradually you end up finally reaching to a single group, and that's called this agglomerative. And this is from bottom up, means that from build up from single observation up to one single group. So you compute all pairwise distances. So actually here it requires some kind of distance measures. Okay? After this slides, I'm going to jump to that the next class now. So talking about distance, I probably should put it there. Put it here. Okay? So compute all pairwise distances among groups. And of course, there's way to compute distances among groups. Okay? There are different methods, co-linkage method. Okay? This method, you can link together with the shortest distance, you can link together with the longest distance, you can link together with average distance among other methods. Okay? And then you combine the closest pair of groups, and these two groups will form a sort of, I should say, the parent group, right? Okay. So we compute intergroup distances after this two regrouping. Okay. Maximum, minimum. So here this is the distances. Okay. The maximum distances or minimum distance or average distance is rule. Okay. In clustering terminology, there are particular name for that. Maximum is also called complete linkage. So the way to compute this intergroup distance is called a different linkage method. That's what it's called in clustering. Okay. Maximum linkage is also called complete linkage. Okay. So it's a different name for that. Okay. This is complete.
Maximum.
That's just a different name. Complete linkage or compact linkage. Okay. Basically, it's telling you that to find the distance between two clusters. Okay. You basically find the longest, the distance, the maximum distance between the members in these two groups, and this will measure the distance between these two clusters. Okay. Okay, so that's called the maximum linkage, and then there's a minimum linkage. This is called minimum, also called single linkage. Minimum linkage basically link together the shortest distance. Maybe I should do that. Okay, what is the shortest distance? Okay, maybe this, right? What? Maybe this. That's a single linkage. Okay. Single linkage is defined by the minimum distance among all pairs of objects from these two groups. Okay. So that's a single linkage. And finally, average linkage, just by its name, you know what that means. Okay. Average linkage basically compute. See, here you have this 1, 2, 3, 4, 1, 2, 3, 4 all together. There are 16 match up, right? So take an average of these 16 distances. That would be average linkage. Okay. So actually, to just combine two clusters, okay, the different linkage can probably produce a different the outcomes. Okay. And basically, you continue until all objects united into one group. Usually, that the final result that this all objects united into one group at a very great distance. Usually, probably not the case. That's not what you want. Basically, they don't just cut down the result. Okay? And you analyze the result in a hierarchical tree. Major branches of tree could be a cluster of interest. Okay? So basically, this is a agglomerative hierarchical method. Okay? Do I have the device it there? I didn't develop this as like extra Krasnov bar. I use the Krasnov. I had it in the other course I taught. Okay. I use only this graphical pencil here. Maybe you can just look at that and then just get the idea of this result. I think I put it up in Krasnov. Okay. I have this cluster one, I guess. That's the one. Don't look at this one. Here you can spend time more on this, but here I do have this in cluster 2 of this one. Okay. Here, these are some there are two objects. Suppose that, well, at the moment I don't use the Euclidean distance, now regular distance measure. Okay, is the difference in the distance between two objects, the difference in x coordinate squared plus the difference in y coordinate squared. Taken square root, that's a Euclidean distance. Okay, so here these are distance measured between object 1 and 2. Okay, you can actually calculate that. Okay. So the x coordinate square plus the difference x coordinate square plus the square of difference in y coordinate square root that. That's the distance. Okay. Now we take this distance measures of this individual variable. Okay. Let me use this graphical to make it easier to show that. Originally, in this case, we have this total of 6 objects or 6 observations. Okay. Originally, each one forms its own group. Right? This is so-called agglomerative algorithm. Okay? And first of all, you find the one with the shortest distance, the pair. Okay? So here you can compute among these 6 clusters. You have 6 choose to distances to calculate, and then this pair is produce the shortest distance. Okay? So these two will first cluster together. So originally you have n clusters. In this case, 6 clusters. Now at the first step, it's just at the first step, it's down to 5 clusters only. Here, this is 1 cluster, right? Okay. These two are combined at this distance, 2.24. Okay. And then here there are 4 other clusters. So total of 5 clusters. Of course, then it depends on what kind of linkage you have. Suppose now we look at a single linkage, meaning that we look at this minimum distances. Okay. So here the distances between all these other objects are easier, but the distance between any object out here with respect to this, you have to calculate minimum distances. It's very hard to tell from this. Probably the minimum distance is, let me see that. Okay. The minimum distance between these two are this, and probably the next shortest distance will be produced by this, right? More likely, isn't it? Okay. This, I've forgotten which one will be. Yeah, that's the next one. Okay. So next one here between 1 and 4, we have this distance of 2.83. It looks like this is another candidate, but you can see the distance between this cluster and 3. We look at 2, 3, and 6, 3, and see that. Look at the previous slides. You can actually see that. Okay. What was that? Between 2, 3, and 6, 3. Sorry. Okay. Between 2 and 3, the distance is 3.61, right? And between what is the other one? 3 and 6, that's 3.16. So the distance between cluster 2, 6 to 3 is 3.16, right? Okay. So that's how we calculate this is 3.16. The distance here is 3.16. Will be given by this 3.16 here. Okay, but these two clusters are with a shorter distance. Okay, so the closest two individual will be clustered first, right? So now at this stage, you actually form. There are 4 clusters now. Okay, so here like 1, 2, 3, 4. There are 4 groups. Okay, and you continue on this. What is the next one? Is going to cluster these two together, right? At 3.16 distance. Okay. So next, we'll cluster this together as one group at this distance, 3.16. I guess the distance between that will be given by 4 and 5. So what is the 4? What is distance between 4 and 5? To go back and forth. Between 4 and 5, that's 5.10, right? So that's why here we actually didn't. This is the step that we see here. Because the distance from this cluster to this is 5.10. Here this is 3.16. So here, this cluster and this R was the shortest distance, right? So we cluster them together. Okay. So next one, now at this stage we had 1 cluster, 2, and 3, right? There are 3 clusters. Okay. And still continue with a single linkage. Next one, of course, we're going to cluster this together, of course. Okay. So here, now it's down to 2 groups, right? So build up, and finally, now you have 2 clusters. Finally, these 2 will be joined with the shortest distance, because now we're still using single linkage, okay? So these 2 clusters will be joined together. Shortest distance, most likely will be between 6 and 4, I think. I already forgot that. Okay. Yeah, 6 and 4, right? So finally, the distance is joined at 8.94. And the so-called dendrogram basically is the graphical representation of this, the building up into this single group. Okay? That's called the dendrogram. Okay? You can see that next. Okay? So next step, you can see that 2 and 6 was first classified at a distance. What was that again? At distance 2.46, right? 2 and 6 were first clustered together, right? At distance 2.46. They're 2.24. So here the height here, this is 2.24. And 4 by 1 and 4, they are clustered together with this distance, slightly less than 3, 2 point something. Actually, we've seen that from there. Okay. The next 2 things, 2.83, right? 1 and 4 clustered together, 2.83. The next thing is to cluster the 2,6 group with 3 with the distance 3.16. That's how you see this, okay? 3.16 here. 3 is clustered together with 2,6. And finally, 1,4 will be joined with 5 with this distance, 5.10. And finally, the last one, okay, they are joined with this distance. The final distance was the 8.94. Okay. That's how it was. Okay, it was combined. This is called dendrogram. Okay, so here this is a sort of a tree diagram representation of this procedure. It doesn't mean that you always have to come up with only one group, right? Okay. Of course, the method where to cluster into 2, how many groups really this is major subjectivity, really a subjective assignment. And it's good not to use just one method like single linkage. You probably want to try other linkage as well. And very likely it's going to produce a very similar cluster, similar groups. Okay. And if there's some clusters like shared by different methods, that means it must be a very important one, right? Look at the result. And here this is complete linkage. You can actually see that. Okay? Complete linkage call for to cluster to measure distance between 2 clusters, you use a maximum distance. But originally they are on its own group. Okay? The 2 clusters with the shortest distance will form together. Still, the first step will form 2 and 6, right? There's no doubt about that. Okay? And the next stage is still cluster 1 and 4 together, isn't it? Right? Okay. 1 and 4 still clustered together because the distance between 3 to 2,6 will be the maximum distance, 3. What was that again? 3.61. That was 1. Okay. Actually, that would be the next one that would class 3.60. That would be the next one clustered together. This complete linkage. But the distance between this cluster 2, 6, and 3 is measured by the maximum distance, not the minimum distance. Okay. And then this 3 will be clustered together. And then these 2 will be joined united in one group using the longest distance. That will be between 3 and 5, I think. Okay? Right? 3 and 5, right? Okay, so that's complete linkage. Okay. So here, you get an idea of this different method. I think I can continue on this, looking at average linkage. I don't have to show everything here, okay? So here, this is example of showing this in the algorithm in action. Okay, look at this. This is a growth motif. So we build up the tree like this, and the question is how many clusters you want to form. Suppose you cut a tree at this distance. Okay. Usually, probably according to your background knowledge, you probably want to cut a certain distance that you think that probably still should be considered as a nature grouping. Let's say you're going to cut here, it's going to form two clusters, right? Two clusters. If you cut a tree at the height, say 5, then you're going to form 3 clusters in this case. Okay. So 3 clusters, one is formed by 3, 2, 6, and the other one was formed by 1, 4, and 5 would by itself form a group. Okay. I'm going to show an example. You can actually use this clustering algorithm to apply on even the supervised learning, and then look at the result. It's pretty interesting. Look at that. Okay. Of course, in supervised learning, we already know the class identities. It would be nice to use that and see the agreements of the cluster result and the actual cluster, the actual classification. Okay. Before I turn into the distance measure, let's look at this so-called divisive cluster method. Okay. That's why I really needed to spend the time on this cluster package. It's a really nice package. There's a lot of different methods and graphical methods presenting the result. Okay. Divisive cluster procedure. If you look at this package, they have all these friends names. This Diana, Clara, and Fanny, or different kind of names. Basically, this is acronyms of some algorithm. And there's a DAISY function based in measuring the distance between objects. It's not different things. This is short for divisive analysis cluster. Okay. That's short for that. Okay. Was developed by these 2 authors, okay. And in fact, that package was also developed by these 2 authors. Okay. Basically, start with a single cluster, the entire set of n objects as a single cluster, and start to divide, okay, until reach just each object by itself. Okay. So it's top down. Okay. So in each step, cluster with the largest diameter is selected and divided into 2 clusters. Okay. Of course, here we have to find a way to define diameter. Okay. And the diameter is defined as a diameter of a cluster basically is maximum distance of the similarity. Okay. Among all objects within the cluster. Okay. And then you find object within this cluster having the largest average dissimilarity. Okay. Object within this cluster. This is sort of an opposite way of something called Mendoids, because there's another cluster method. Okay. In this package, cluster is called partitioning. That's a partitioning method. Okay. It's called partitioning. PA. Partitioning is this is PAM. Okay. There's an object called PAM. It's called partitioning around Mendoids. Okay. Mendoid within the cluster means that a particular object, okay? What is the existent object? This particular object with the most similarity, average similarity with all other objects within the cluster. But here we talk about, in this case, here we talk about this so-called a sprinter, sort of this, how do you call this name? I think there's a particular name for this particular object. I don't know if they call this sprinter objects or not. Okay, but anyway, object within this cluster having the largest average dissimilarity. So this is like an opposite of this so-called Mendoid. Mendoid, in a sense, is kind of provided a sense of the center of your cluster, right? Because this is the particular object within the cluster which is the most similar with all others. With the average, the largest similarity, average large similarity with all others, or shortest average distances with all others. Okay. Actually, we'll talk about that in the future. Okay, this is not hierarchical method. This is partitioning method. Okay? We'll talk about that later. But anyway, the idea is finding object, okay, which is most different. Well, I was put this way, right? Most different than all other objects, and this were initially so-called splinter groups. Okay, and this object was isolated and try to attract other members within the same cluster to form a partition. That's a basic idea of that. Okay. An object within this cluster reassigned to the splinter group, it is closer to the splinter group than to the old party, means the original parent grouping. Okay. And this step is iterative until you reach all all the objects by itself. Okay. That's called divisive. So basically, let's look at this online example. I do have that. I do have an example that is everything. Let me do that. This is divisive. Okay. So originally, this is one big cluster, just one. So all observations are considered from one group from the very beginning. And the diameter is measured. This is diameter. Diameter basically is the maximum distance, okay, among the pairs of objects. Okay, so that's diameter. Okay, and then you find the splinter elements. Okay. Basically, at first, this is the element which is most dissimilar to all others. You can actually calculate. For example, you can calculate average distance of phi to all other phi objects. You can calculate average distances from 4 to all other objects. And phi gives the largest average distance. Okay? So that would be this initial splinter group. And this one starts to attract objects to it to form a group. Okay? So that's the idea. Okay? This is a really interesting idea, right? We call this a separatist, something like that, right? So they try to say, okay, now here I'm very different than others. Follow me, something like that. Okay. So first of all, this one. Okay. These are the two. These two are closest to this new group. Then. On average, of course, on average, right? This, of course, the distance between 4 and 5, there's only one distance here. Okay, the distance of this is shorter than the average distance of 4 to all other groups in all parties. So that's why 4 will be attracted to that. And similarly for 1, but not this one. Okay, 2 is closer to on average distance to all other groups in the all party, meaning the original one cluster, than this to 5. Okay. So that's why 1 and 4 will be formed together. Okay. And likewise, you can also say that 2. I think I skipped some steps here. Okay. Probably I should show all steps. Okay. Anyway, 2, 6, 3 will be formed in a likewise manner. Okay. And then finally, okay, within that, you also find another splinter. Okay. Within this cluster, and then do this recursively, right? Okay, recursive within this cluster, phi again is most dissimilar with all others, with average, with the longest average distance than other. So here phi is again, okay, so try to separate, but then phi will be separated with the other 1 and 4. Okay? And do likewise, and then here this is another one. Within this cluster, this is a small cluster. 3 is most different than the other 2. So this will spin the group and see if it will attract new membership. It turns out not. 2 and 6 will still remain themselves. Okay. And finally, of course, it's very easy with two objects within one cluster. Be just divisive, simply just divisive. Okay. So finally, down to that. Okay. And all these distances here I put down all these distances. These distances will be recorded in the dendrogram. So we produce dendrogram like this. Okay. First, in one group, they are in one group with a diameter. What was that? A diameter was 16 point something, right? This is diameter for a single group. Okay, and then 5 initial splinter, and then you can see the diameter for this group. Right, this is diameter for that group. Okay, this is diameter for group 1, 4, and 5. Okay, and here this will be diameter. Okay. So basically, this is idea of this divisive nesting. Okay. So I'm going to talk about distances. No time. It's going to be here. I talk about these distances in this class notes. Okay, there. In the distance measures in first section, I also look about. I separate this from others. This is called dollars and distances. Okay. Yeah, actually, this is more realistic because basically this data with a mixed types of input variable, okay, you can apply these distances. Okay. The regular Euclidean distances or other Euclidean distance related, okay, you know, we cannot use this. We cannot use this type. Okay. Basically, they call for numerical variable, but this one you can have mixed types of variables in there. So the goal is distance. I'm going to talk about that. Okay, let me start now. So project number 4 in the class case study due next Tuesday, right? See, we kind of far behind. I originally planned to have 6 case studies, right? Plus 1 final project. Looks like we either start with 5 case study with a final project, or maybe 4 plus 1. So I will readjust the scores. Anyway, in any case studies, I kind of play with the percentage, so it's very easy to adjust. Okay, so let me start now.
Yeah.